Okay, here we are. We have a problem which says that 5 forces are acting on a hot air balloon. The first is F1 equals 36.1 newtons at 34.4 degrees north of east. Well, as I read this problem, the first thing I'm going to do is create a free body diagram which shows the forces, and we know that whenever we draw a free body diagram, we draw every force, no matter how it points. Every force starts with its starts with its tail at the object. So my object here, right, is in blue. It's a blue dot. Every object is a dot on a free body diagram. And, I mean, I've just made up these fake forces, and that's not what they'll look like, so I better take them away. But we just draw the forces stemming from the dot and extending out in the direction where they point. So each force is an arrow. That's what free body diagrams are. So we have the 5 forces. The first, F1, it's 36 newtons, and it's north of east. So, just so we know, north, east, south, west. So if it's north of east, that means it's not east, like that, but it's north a little bit from east. So down here, this would be south of east. This would be straight west, or due west. Something like this would be south of west, and that would be north of west. So that's how the conventions are phrased. Let me take this away. So it's north up from east, right? So it's up some amount. And we'll estimate the angle like that. Okay. There's F1. As I draw my picture, I'm also going to list these values. F1 is 36.1, and theta 1, the angle, is, I better draw it into my picture, theta 1, and it's 34.4. F2 is due west, so F2 is like this. And how big is F2? F2 is 32.4 newtons. F3, and F2 doesn't have an angle, see, because it's already on the x-axis. It's perfectly west, due west. The third force, F3, is 41.3 newtons at 53.2 degrees south of west. So if west is over this way, it's kind of south a little bit of west. But whoops, I have to make sure that I draw it starting at the blue dot. So it's south of west. Not north of west, but south of west. Right? North of west would be up here. That's not what it's doing. It's south of west. And what are the numbers I put for F3? Let's see. Let me move this over. F3 is 41.3, and its angle is 52, 53.2, like that. Okay, good. F4, due north, like so, 21.5. Okay. The final force is F5, which is due east. F5, whoops, I forgot to draw in theta 3. There's theta 3. And that due east force is 119.8. Oh my, what a big problem. So many forces. But that's okay, we can handle it. We have to find the net force, right? And find the angle at which it points. Force is a vector, it has a direction and a magnitude. The angle is the direction, and the magnitude is the number of newtons that the force has. So net force is what we must find. Here is our method. We are going to find the net x force, then we're going to find the net y force, and then we're going to use the Pythagorean theorem to find the net force. But before we do that, let's go around each one of these 5 forces, right, one by one, and see whether it's already on the x or y axis, or whether we have to break it into components, resolve it into its components. So F1 is our first vector. F1 is at an angle. It's not on an axis. So we will have to represent F1 with components, right? F1 will have, let's see, I'll use green. It'll have a y component going, well wait, first let me say. F1 will have an x component going like this, and I'll call it x1 for the x component of force 1. And x1 is different from F5, right? These are 2 different forces, which are both pointing to the right. And it'll have, let's break that up. So there will be this x component, and of course, components, that's just a fancy name for the legs of a right triangle, right? Component is just a fancy name for legs of a right triangle. So there's an x leg and a y leg, but with force diagrams, free body diagrams, we draw each force so that it stems from the blue dot. So I'm just going to move my y component over like that. Good. Now that I've done this, I'm taking F1, I'm taking F1 out of the picture because I don't want to represent F1 twice. And so I can either represent F1 as an angled force, or I can represent it as its components. It's more useful in solving the problem to draw it as the components. So there I've drawn the components, I've erased the original F1, so I don't get confused. F2 is next, right? So we've done F1, F2 is on the x-axis, so there's no need to resolve it into vectors, into its components. F3, we see, is not on the axis, so we must resolve it into its components. So there will be an x component, that's not very well done, an x component like that, excuse me, x3, and that stands for the x component of force 3. And there will be a y component that goes down, and I'll call it y3. Okay. Of course, x3, x is just the x leg of the triangle, right? The x component is the x leg of the triangle, and the y component is simply the y leg of the right triangle. Yeah, components always make a right triangle. So we know that these components both have to be drawn so that they stem from the blue dot. So I've moved the y component over so it stems from the blue dot. That's the rule for free body diagrams. And I've taken F3 out of the picture because now, in my drawing, I've represented it with its components, which I resolved. Right? I've resolved the vector into the components. So what we have here is something workable. This is our goal, right? Because now, if we look at the other forces, F4 and 5, F4 and F5 are also on the axis, so every single force that we've drawn in, whether it's an actual force or simply a component, every one of those forces or components is on the x or y axis. So we can sum the x forces, and the sigma means take the sum of, add up all of the individual x forces, right? So this is a fancy way of saying find F net x. This notation and this notation, those are identical. So I'm going to sum all of the x forces, okay? And then I'm going to sum all of the y forces, okay? And we'll see why we do this. So when I sum the x forces, I have to look at each force and either make it positive or negative based on whether it's rightward or leftward pointing. So I see x1 will be positive, that's to the right. F5 will be positive, x3 is a negative force, this is a negative force, F2. Okay then, I'm ready to go. Positive x1 plus F5 minus x3 minus F2 is what I have. Okay? Like that. So, what do I need to calculate? Well, x1, this is an x component of force 1, so I look over here, and I'm going to write x1 as, well, it's an x component, so it's r cosine theta. And what is r? R is the thing that was at an angle. R is the force, 36.1. That's what was at an angle. That's what we broke into components. Right? Remember, r, the force was up like that. That's the hypotenuse. So what I have for x1 is 36.1, and I'm going to leave off units for now, for the sake of space. Cosine theta 1, which is 34.4. Okay. Then I have f5, which I have to add, so here it is, I found it, 19.8. Good. Now, I'm going to run out of space. Now, some of the forces in the x, some of the x forces. Now I have to subtract x3, that's another x component, right? And every x component is r cosine theta, provided that theta is the bottom angle of the right triangle. So I have another r cos theta, this time for x3. So I look over to my chart, and it's going to be, r is 41.3, cosine 53.2 degrees. Good, very, very good. And the last thing to do is subtract f2. Whoops, look out. Gotta subtract f2, which is 32.4. Good. And if I plug this into my calculator, make sure you're in degrees, because my angles here, these are expressed in degrees. That's what the little symbol says. So my calculator has to be in degrees mode, so it knows I'm plugging in a number of degrees, and it is 36.1 cosine 34.4 plus 19.8 minus 41.3 cos 53.2 minus 32.4. I forgot to add close parentheses on my angles, and I hit enter. What do I get? I get that the sum of the x forces is negative, that means to the left, 7.55. Beautiful. 553. And I'm not going to round this value yet because I don't have to report anything till the very end, and so I don't have to round anything till the very end. No early rounding, that's bad. Alright, get rid of this. So I'm going to move my answer up here. The next we'll do is we'll sum the y forces. So I look at my chart, right? And just as I looked and found all of the x forces, now I'm just going to look and write down all of the y forces. So I see clearly there's 3 y forces. There's f4, there's y1, that y component, and there's y2, right? So remember, we must consider direction. Any upward force is positive, so this is positive, and this is positive. And any downward force, y3, is negativo, negative. That's probably not really a word. Okay, and we can add up then all of the y forces. We can sum the y forces together. And we have a positive f4 plus a positive y1, and then we have a negative, so it's minus y3. So f4, look at the chart, right over here. That's a fancy chart, nice chart to have, huh? Sure is convenient. So it's 21.5. y1, that's the y component of force 1. So I look here. It's an r sine theta, right? Y components are equal to r sine theta, provided we have the bottom angle, which we do in this problem. So y1 is simply r sine theta degrees minus, looks like a sad face, minus y3, that's another y component, so again, I look here, minus r sine theta. Good. And actually, I'm done with my chart now so I can erase. So I plug this into my calculator to find what the sum equals. What do I get when I sum these forces, these y forces together? Minus 41.3 sine 53.2. Did I close all the parentheses? If I've done this correctly, and there's no guarantee. No, there is a guarantee because you can check it yourself. It's 8.825 newtons, right? I mean, is it really just 25? Dot, dot, dot. There's a lot of decimal places. But if we round, if we round to, if we round to this place, we'll be fine. We won't have an incorrect answer if we give this many decimal places. Okay. So the sum of the y forces, when I add up all the individual y's, this is individual y, this says add them all up. When I add up all those y forces, I get a positive, that means up, 8.825. Erase the work. Here's why we've done this, okay? When you break the components, when you resolve the vectors into these components, and you find the net x force and the net y force, we can draw one final right triangle, which is what I like to call the final F-net triangle. So we're going to draw the net x force as a single vector, then we're going to draw the net y force as a single vector. So the net x force is negative, so it's to the left. Here's the net x force. The net y force is, it's positive, so it's up. Oh, bring it down. Positive, up like this. Here's the net y force. And let me make this below. So F-net is simply the vector sum of the net x force plus the net y force. In other words, F-net is simply the net x force plus the net y force. And let me move this over to here. But when I write this equation, what I really mean is these are vectors, so I use those funny half arrows to say vectors. And vectors are not added like scalars. You can't just say, F-net is 5 plus 4. These things have direction, and so we have to add the vectors graphically. And that's what this is for, to do the graphical vector addition, right? If you try to add this plus this, you will get into trouble because you failed to account for the direction of these vectors. Right? If you try to add negative 7.553 plus 8.825, then you're treating these vectors as scalars, and that's the wrong way to go. So, whoops. Okay, so we have to take a vector sum, which means we have to use the Pythagorean theorem. F-net is this. Of course, any y component is perpendicular to the x component. So I have here a right triangle, and the way I'll find F-net is by taking the square root of negative 7.553 squared plus 8.825 squared, and that'll give me the value F-net. And what I calculate in my calculator, 8.8251 squared plus negative 7.553 squared, I get 11.6 newtons. 11.6. And that's the right number of sig figs to include, because all of the givens had 3 sig figs. So, yeah, 3, 3, 3 all the way. They all had 3, so my answer will have 3, just following the sig fig shortcut. Now, the last thing to find is theta. So we have to remember there's an equation we use. Theta is always inverse tangent. Well, assuming theta is the bottom angle, which yes, I'm finding the bottom angle here. That's a bottom angle. theta is the inverse tangent of the y leg over the x leg. X. Fx. Okay then, that means theta is calculated by plugging into my calculator inverse tangent of 8.825 over... Now I'm just going to make this positive, and you'll see why in a second, but make it positive. Just plug in positive values only into this equation. So I go inverse tangent on my calculator, 8.825 over 7.553, and I get 49 degrees. Good. So, I made it positive. Whoops, let me bring that back for a second. I made this positive, and the reason is because I can worry about the direction that this angle is pointing in. I can worry about that as a separate matter. Here's what I mean. If I look at my F-net triangle, I see that this F-net is up from east. So it's 49 degrees, right? 49.4, let me add another sig fig. Up or north of east. And now I don't have to worry about a negative sign because I've expressed the correct cardinal directions where it's pointing, where the 49 degrees points. I've expressed that using these cardinal directions. And that's the best way to go. Plug in positive values into the equation, inverse tangent of net y force over net x force, and then just use your cardinal directions to express the proper way that the angle is pointing. And of course you get those cardinal directions by looking at your picture. Your final F-net triangle tells you that. So that's it. These are kind of longer problems, but if you have good organization, you can actually solve them pretty quickly, and you find that it's the same kind of pattern over and over for these types of problems.